Assalamu alaikum warahmatullahi wabarakatuh. My name is Muhammad Hayyan Al-Sibai. I am member of Faculty of Engineering Technology, and I'm here today to represent for you the final part of the module 10 of our course current analysis power consumption. The module 10 is actually is an introduction to basic AC fundamentals. So by the end of this part, you are supposed to understand what is the phasor. I introduced the phasor for you. You see the waveform average value and effective value RMS, and AC voltage and current measurement. So we'll speak a little bit about how to measure the current and voltage. So last time in the part 2, I give you the definition of the phasor. So a phasor actually is a vector. This vector is not normal vector, it's a rotating vector. So when this vector is rotating, the projection on a vertical axis can be used to represent sinusoidally varying quantities. So this is a vector. When it's rotate, the projection of it is a sinusoidal waveform. Why we need this vector? Because let's see how it's generating the sinusoidal waveform. So as you can see here in the graph, when it's starting with the position 0, the value is 0. Now increasing 30 degrees by time, you see the value is increasing until it's perpendicular. So when it's perpendicular, it reaches its maximum, which is 100 voltage. Now continue rotation, you see the sinusoidal waveform is decreasing, the value is decreasing, and until it reaches 0 again at the value 180. Completing the cycle, it's complete the sinusoidal waveform. So if we look at the complete graph now, as you can see here, okay, as you can see in the complete graph, so we have the 4 graphs together. So you see one cycle is generating one sinusoidal waveform. So phasor actually is easier to represent values in the electricity and actually in the sinusoidal waveform. So for example, the shifted sine waveform is easier to represent using the phasor. So phasor may be used to represent the shifted waveform. Let's say we have V equal to Vm sine omega t plus minus theta, or for the current, I equal to Im sine omega t plus minus theta. So as you see in the figure, if the phasor angle is positive, so it's shifted, it represents that the sinusoidal waveform is shifted left. If it's negative, it means that it is shifted right. Also, it's very useful when we need to explain what's called the phase difference. So phase difference, if we have two sinusoidal waveforms, it's actually the angular displacement between different waveforms at the same frequency. So if we have here, for example, always the voltage and current have the same frequency. So if they are starting at the same point together, as you can see in figure A, so they are in phase. In figure B, you see the current is starting before the voltage. So we say the current leads. The current leads the voltage. In the figure C, the current lags because voltage starts before the current. I mean, it's passed through 0 before the voltage. So the term lead and lag actually can be more understood using the phasor. So first, let's define what is lead and lag. So by definition, the waveform generated by the leading phasor leads the waveform generating by the lagging phasor and vice versa. Now, let's have a look to this figure. As you can see, Im has angle theta, V has angle 0. So if we represent the sinusoidal waveform of them, we will see how the current is coming before the voltage, and it's very clear from the phasor that current is before the voltage. So the current is leading the voltage. So Im leads phasor Vm. Thus, current IT leads voltage Vt. But keep in your mind that the phasor is drawn at the initial time, but the value of voltage or current at any point of the waveform having negative and positive value. It's always changing between negative and positive, represented by V and I. So when we use the small letter, actually we are showing the instantaneous values. When we use the capital letter, we use the, which is used by the phasor, it's to represent the Vm, the maximum value, for example. Okay? Now, we need to, as I said, like the voltage and current are always changing. But when we look to our blog at our homes, for example, we say that we have 240 volt. Okay? In Malaysia and other countries, it's 220 or 240. If we go to US or Japan, for example, they said this plug is 100 volt. Okay? So if it's like continuously changed, why we use this value, 100 or 240 volt? Actually, there is no single numerical value that truly represents the waveform over its complete cycle. AC quantities are generally described by a group of characteristics, as we saw before, including peak, average, and effective values. So, thus the value that we are showing is the average value. Let's see how the average is calculated first. So the average, let's say we have a test mark. Okay, we have 80, 60, 60, 95, and 75. If we want to calculate the average for them, it's equal to 80 multiplied by 1 plus 60 multiplied by 2, because we have two instances of 60, plus 95 multiplied by 1 plus 75 multiplied by 1, divided by the number of the marks, which are 5. The result is 74, which is the average. Now, if we try to plot the things, so we have 80 as one part of time, or one part of any unit, we call it the base. So we have one base for 80, two bases for 60, one base for 95, and one base for 75. Okay? So we can say, in other words, the average can be represented as the area under the curve, divided by the length of the base. In our case, the length of the base is 5. Now, in other words, in electricity, usually the average is representing the DC, the direct current. Average values are also called DC values. So, DC meters, if you have a DC meter, it indicates the average value rather than the instantaneous value. So, when we measure a non-DC quantity with a DC meter, the meter will read the average of the waveform, that is the value calculated according to the last equation. Okay? So, if you mistakenly trying to, for example, measure using the multimeter the voltage, the AC voltage, and if you putting the function on DC, it will give you 0. Why? Because the sine waveform is symmetrical. So if you apply the previous equation, which is the area of the under the curve divided by the base, the average of sine omega t plus minus theta, 2 omega t, cosine omega t, whatever, it's always 0, because there is positive part which is exactly similar to the negative part. So actually, the value that is read on the plugs, which is 240 or 100 volt, is not actually the average. Actually, it's called the effective or RMS value. Okay? So what are the effective values? We define them as an effective value is an equivalent DC value. It tells you how many volts or amperes of DC that a time varying waveform is equal to in terms of its ability to produce average power. So in other words, that when we say that this AC plug is giving 240 volt AC. That means it's giving power equivalent to similar DC power supply, which is having 240 volt DC. It's giving the same power. So a 240 volt in the homes means that the sinusoidal voltage at the wall outlets of the home is capable to producing the same average power of 240 volts of a steady DC power supply. So, what is the relation between effective or RMS and the peak or peak-to-peak values? So, by definition, the effective value of current I is that the value of DC current that produces the same average power DC. So, it's the same average power. So, DC, B average equal to P equal to I square R. This is for DC. I and B and R are all values. In AC, we have the same calculation for power. So PT at any time equal to I at any time square multiplied by R. We replace using the sinusoidal waveform. So it's Im sine omega t square R. We do some preparation or regulation for the equation and we get it's equal to Im square R multiplied by half multiplied by 1 minus cosine 2 omega t. It can be rewritten as Pt equal to I square R divided by 2 minus Im square R divided by 2 multiplied by cosine 2 omega. If we take the average of this one, the later part after the minus is 0. The average of it is 0 because the average of the cosine 2 omega t is 0. So the B average in this case is only Im square R divided by 2. Now, if we plot things, so we need to calculate the average power. Since power is I square, so it's always positive, so it has an average. Its average is not 0. Its average actually is Im square R divided by 2. If we take the DC, as you can see, the DC is stable all the time, so it has the average power is P. Now, if we calculate for them, so B average for AC equal to B average of DC. This is how, by definition, how we calculate the RMS. So, after cancelling R from the previous equation, we get, as you can see, I square equal to Im square divided by 2. I is for the DC and Im is for the AC. So, with some regulation, we get I equal to Im squared divided by 2 equal to Im divided by the root of 2 or equal to 0.707 Im. So actually this is the relation between IRMS and Im, the peak value. So current I is the value that we are looking for. It's the effective value or of current I. We use notation I effect. So, I effect equal to Im divided by the root of 2 or equal to 0.707 Im. And similarly, we can see that E effective and V effective equal to E effective equal to Em divided by the root of 2 or 0.707 Em, and E effective is Vm divided by the root of 2 or equal to 0.707 Vm. So this is actually the value that a multimeter is measured. So we have two devices to measure the AC values. One of them is the multimeter. It should be adjusted to AC function, and the oscilloscope. There are two basic classes of the AC meters. The one which is measure the RMS correctly for sinusoidal waveform, and it's called average responding instrument. The other one is called is actually measure the RMS correctly regardless of the waveform. It's called the true RMS meter. The most common meter in the actually is from the average responding meters, which is more cheaper. The other device to show, actually, it's not only to measure, it's also to show the sinusoidal waveform, which the oscilloscope. The oscilloscope actually is the screen of the oscilloscope are scaled in volts vertically and in time horizontally. So we have the horizontal one, the horizontal axis is for time, and the vertical one is for voltage, to permit visual study of the waveform. Most modern oscilloscopes have digital technology rather than CRT design of few years ago, and have many more features for calculation. Now, before we finish this module, somebody may ask why we are using AC if by definition we say that this AC plug is giving us the same power as the DC plug, which is 240, and we use the DC as our reference. Actually, there is very important thing that make us to use AC, not DC, in our homes. There are actually two factors, two important factors to use AC. The first one, if we look at the power. So power equal to V multiplied by I, and it's calculated by watt. Okay? So the higher the voltage, the lower the current. And if we make the power is stable, so current is high, voltage is low. Voltage is high, current is low. So the lower the current, the higher the voltage, and vice versa, of course, at the same power. So for using very high current, the thickness of the wires that transfer this current should be thick. Okay? So more current, more thickness. That's why if you look at, for example, the near your house, there is one room which is related to TMB. It's telling you that be careful, it's high voltage. Why they make the voltage high? Because no need to high current to transfer the electricity. So the transmission line would be very expensive. That's why high voltage are used. We use thousands of volts. It's usually in kilovolt to transmit from the generating plants with relatively thin wires. Now, when it reaches our homes, we need to use another impact which make us use the AC, which is the transformers. DC is not used on transformers, but AC is used in transformers. Transformers actually is a device that change the voltage according to the rate of the coils. So they only work in AC. That's why we use AC to generate at the generating plant very high voltage, transmit it using thin power, and then when it's necessary to lower the voltage, the current, and to raise the current, then we can use the transformers near our homes. So I think like this we finish our module. As the summary of this part, we study the introduction to phasors. We see how phasors represent many things instead of using the sinusoidal waveform. We see the AC waveform average value and effective value, or RMS. We see the AC voltage and current measurement tools, and we understand why actually we are using AC, not DC, in our houses. Thank you very much for attending this module, and here in this you can see some references for more study if you want to study more about this topic. Thank you very much.